Welcome back to the Deep Dive. We're here to bring you the crucial knowledge you need, distilled from the very best sources out there. Today, we're setting our sights much further afield than usual. We're going beyond the moon, beyond the planets. This is our deep dive into the practical side and also the sheer joy of looking at deep sky objects. Think galaxies, nebulae, star clusters. And this is really aimed at the serious amateur observer.
That's exactly right. So if you've already got the basics down, you got a telescope, you've got your charts,
Yeah.
and you're itching to move past just seeing little fuzzy blobs and actually start picking out structure. Well, this deep dive is definitely for you. We've been really digging into Stephen R. Coe's brilliant book, Deep Sky Observing. And Coe's very clear, this isn't for total beginners. We're skipping things like defining light year. We're jumping right into how you, the intermediate observer, can get the absolute most out of your time under the stars.
Yeah, and Coe is, well, he's the perfect guide for this, isn't he? 40 years as an active amateur astronomer, mostly observing from Arizona, which, has some famously dark skies. And maybe even more importantly, he spent 2 decades chairing the novice group for the Saguaro Astronomy Club, they call it SAC. So our mission today, really, is to boil down the expert advice Coe gathered over those 20 years, answering questions from real club members. We want to help you maximize your experience out there and turn those faint fuzzies into, well, genuine cosmic wonders. Okay, so before we even touch on things like aperture or magnification, we really need to talk about preparation. It's fundamental. You could have the most amazing telescope, the biggest scope in the world, but if you're freezing cold, exhausted, or in a lousy spot, well, you're just not going to see much. So let's kick off with what Coe calls the non-negotiable first step, getting yourself to a dark observing site.
This is absolutely critical. It's probably the single biggest factor in whether you'll have a successful deep sky session. Coe really hammers this home. The difference between looking from, say, the edge of a city versus a truly dark site it's just transformative. He uses a great example observing Sagittarius. From the city limits of Phoenix, even on a good night, you might just make out the bright stars of the Teapot asterism.
Yeah.
That's about it. But drive just a couple hours away, get clear of that massive light dome, and suddenly Sagittarius isn't just a few stars, it's this amazing light show. The Milky Way stops being this faint, hazy band and becomes like a glowing beacon across the sky. That drive, that effort, it pays off instantly when you look up.
And he offers a really smart, strategic way to plan that drive, too. It's not just about distance. He actually suggests looking at those nighttime satellite photos of the continent. You can literally see the light domes, how big they are, how intense. And then comes the crucial rule for planning your observing list for the night. Make sure it lines up with the direction you drove. So say you drive 2 hours east to escape the city glow behind you in the west. Don't waste your precious dark sky time trying to observe objects that are setting over in the west. They'll just get swallowed up by that light dome you literally just drove away from. You've got to focus your attention on the objects rising in the east, where the sky is genuinely dark, untouched by that city light.
That makes perfect sense. And he also tackles something that often trips up beginners, this idea about altitude, the assumption that higher is always better for seeing. Actually cautions against going to extreme altitudes. He says once you get above about 7,000 feet, maybe 2,200 meters or so, it actually starts working against you. The lack of oxygen up there begins to affect your vision. Specifically, it impacts the rods in your retina, the cells you need for seeing in dim light. So any small gain you might get from slightly clearer air is basically canceled out because your eyes themselves aren't working as well. You reach a point of diminishing returns, really.
That's fascinating. And thinking about these trips, astronomy often means late nights, driving to remote places. So safety is a big deal. Coe really recommends traveling in groups. It's not just safer in terms of, breakdowns or getting lost. It's also about keeping your stamina up. He even suggests something a bit old school but effective, using a CB radio between cars. You can warn each other about road hazards, deer, whatever, but maybe just as important. It helps keep the drivers, especially the lead and follow cars, engaged and awake on that long, often very late drive home. #hashtag 1.2 weather wisdom and preparation.
Right. So once you really commit to deep sky observing, you kind of have to accept another role, amateur weather forecaster. Coe is adamant about this. You need to become a dedicated weather watcher. And knowing your clouds is key. He points out that those thick layered clouds, stratus clouds, well, they're usually you're grounded for days, no astronomy happening. But the high, thin, wispy ones, cirrus clouds, sometimes, especially in drier climates like the desert Southwest, they can actually dissipate after sunset. So if you see cirrus during the day, it might still be worth heading out or at least waiting a bit.
And speaking of regional knowledge, he shares this really cool weather prediction trick from the southwest US. It's all about looking at the sky during the day. You check the color of the blue sky. If it looks whitish or maybe just a very pale, washed out blue, that tells you there's a lot of dust and tiny particles, aerosols scattering the sunlight. That means poor transparency for nighttime viewing. On nights like that, he says, you should probably stick to brighter deep sky targets. But if the daytime sky is this really rich, deep, medium to dark blue, that indicates minimal dust. The air is clear, and that's your signal. That's the night to go hunting for those really faint, challenging nebulae and galaxies. It's like a built-in daytime check for nighttime clarity.
That's a great tip. And all this preparation, it really comes down to maximizing your comfort and your ability to focus. Ko gives some classic veteran advice here. One key thing: put your warm clothes on before you feel cold. Once you actually start shivering, your observing precision just plummets. It's hard to hold steady, hard to concentrate. Layering clothes is obviously essential, but he has a really specific gear recommendation for handling equipment in the cold. Rock climbers' gloves, the kind with the fingertips cut out. They let you do fiddly things like swapping eyepieces or changing filters without taking your gloves off completely. Keeps the main part of your hands warm. Brilliant.
Yeah, that's clever. And the last piece of this preparation puzzle, one that people often forget, is rest. Simple rest. Ko points out that a night of observing is really like a marathon. It's not a sprint. Taking even a short nap before you head out, or maybe finding a quiet spot for a quick power nap around midnight. Maybe when your main targets are crossing the meridian and are at their highest point, that can make a huge difference to how well you observe later in the session. As he puts it very simply. A really sleepy observer is not having fun. And, let's face it, a tired observer just doesn't see as much detail. Hashtag 1.3, the art of seeing and note-taking. Okay, so you've done the prep. You're rested, you're warm, you're under that perfect dark sky. Fantastic. Now the real skill development begins, doesn't it? Training your eye actually see things. Ko brings up Sir William Herschel, who famously said that seeing is an art that is learned. It doesn't just happen. And the main tool for learning that art, it's taking detailed, standardized notes. He's quite blunt about it, those early notes most of us take. Things like, wow, cool, or faint, not much there. They're basically useless later on. They don't capture the specific details, the structure you need for comparison or reference.
Exactly. And that's why having a standard system is so critical. Ko introduces the classic NGC abbreviations. These actually started out as William Herschel's own personal shorthand for logging his observations quickly at the eyepiece. They give us a common language, a way to efficiently record what we're seeing in the field. Should we maybe break down one of the more involved examples he gives?
Yeah, let's do that. He gives this string, P, F, P, S, L, E, G, V, L, B, M. What on earth does that translate to, and how does the order work?
Okay, so the order generally moves from the overall impression brightness and size down to shape and then internal detail. So PF means pretty faint, okay, not super bright. PS means pretty small, so it's a relatively faint, relatively small object. Then LE tells us the shape, a little elongated, so it's not perfectly round. And the last bit, TVLBM, that's where the subtle detail comes in.
Gradually.
Very little brighter in the middle. This tells you the galaxy presumably has a slight core, not a star-like point, and the brightness increases gently towards that center. See how much info is packed in there.
That's incredibly efficient. A whole description in just a few letters. Okay, what about something spectacular? Like if you stumble upon an amazing globular cluster, he gives this example. B, Viri, MC.
Ah, now you're talking. That's like hitting the jackpot observationally. The eel means it's very remarkable, something that really grabs your attention. B just confirms it's bright. Then VV means very rich. That tells you it's packed with component stars, just teeming with them. And finally, MC stands for much compressed. That describes the core. It's very dense, highly concentrated. So in just those few abbreviations, you've captured, wow, this is amazing. Bright loads of stars and a really tight core. Concise, specific, perfect for field notes.
It really is a powerful system. And practically speaking, while you're out there scribbling these notes in the dark, Ko has a super important tip. Use only a standard #2 pencil and plain white paper. Seems basic, right? But if you try using a pen, especially red ink, thinking it'll preserve your night vision, well, guess what? Under the red flashlight you need to use to keep your eyes dark adapted, red ink completely vanishes. Poof, gone. So the humble graphite pencil on white paper is the reliable way to go.
Good point. And it's not just about describing the object itself. Ko insists you also need to quantify the conditions of the night. There are two absolutely vital metrics you should record every single time you observe: transparency, and seeing.
Okay, let's break those down. Transparency, that's about sky clarity, right? How clear the air is. It relates to things like haze, dust, maybe thin clouds, anything that affects the contrast between an object and the sky background. And Ku says to rate this on a simple 0 to 10 scale. A 10 would be like a perfectly transparent, pitch black, dust-free sky. This rating directly impacts how well you can see those faint, spread out objects like nebulae or the outer arms of galaxies.
Exactly. And then there's seeing. This is different. Seeing measures the steadiness of the atmosphere. Is the air turbulent or calm? This is absolutely crucial for high magnification views. Think planets, double stars, trying to resolve the core of a globular cluster. If the seeing is bad, the image just boils and shimmers. Coe recommends using the Pickering scale for this. It's also rated 1 to 10. A Pickering 1 or 2 means the star image looks like a big boiling blob, totally useless for high power. But a Pickering 8, 9, or even 10 means the star shows a sharp, stable diffraction disk, maybe even with clear concentric rings around it. Perfect seeing. Recording this number helps you understand later why maybe you couldn't push the magnification past, say, 100x on a particular night. It wasn't your scope, it was the atmosphere.
That makes sense. Quantifying the conditions is just as important as describing the object. And speaking of notes and checking things, we absolutely have to share Coe's cautionary tale about note checking, because even the experts can trip themselves up. It involves a galaxy called NGC 4027. It's in the constellation Corvus. He was observing it one night, and he spotted this faint star, maybe 13th magnitude, sitting right near the galaxy's core. And instantly, his heart starts pounding. He thinks, wow, I found a supernova. You know, the astronomer's dream discovery. He takes super detailed notes, sketches the position meticulously, checks everything, and drives home absolutely buzzing, imagining the discovery announcements.
Oh, I can picture the excitement. So what happened next? Well, being a diligent observer, he starts the process of confirming it. He pulls out all the major references, the big observing guides, charts, and his excitement slowly starts to fade as he checks deeper and deeper. Confusion sets in then. Resignation. He finds the star. It's already known, already cataloged, no supernova. But here's the kicker, the real punchline. He realizes the drawing in one of the most respected guides, the Night Sky Observer's Guide. The very drawing that clearly shot that 13th magnitude star right where he saw it, shattering his discovery hopes, was his own drawing, submitted to the guide years earlier. She'd completely forgotten he'd observed and recorded it before.
Oh my gosh, that is both hilarious and a powerful lesson. You have got to check your notes meticulously, even against your own previous work. It just perfectly highlights why keeping those detailed, accurate records is so essential, even if sometimes they just remind you of things you've forgotten.
Okay, let's shift gears now from the observer's mindset and notes to the actual tools and techniques for finding things out there. Because the biggest challenge, fundamentally, is just the sheer scale of the sky. It's huge. Coe wisely suggests starting simple. Just spend a few months watching the night sky with your naked eyes. See how the constellations move through the seasons, how everything seems to, as he puts it, dance around your home. Get that basic orientation first.
That's good advice. But when you are ready to actually point a telescope, you quickly realize one star chart just isn't gonna cut it, is it? Coe is pretty insistent here. You need several charts, working at different scales. You need what he calls wide field charts. Something like the Bright Star Atlas 2000. These show larger areas, brighter stars, the main constellation patterns. They get you into the right neighborhood. But then for actually pinpointing faint, deep sky objects, you absolutely need deep field charts. Think Uranometria 2000 or maybe the Sky Atlas 2000. These go much fainter, showing more stars, and crucially, plotting the positions of those nebulae and galaxies you're hunting.
Right. You need both the overview and the detailed map. And then you need something to help you aim the telescope accurately. Finder scopes are indispensable. The traditional kind, like a small refracting telescope with crosshairs, they work fine. But Coe is a big fan, and I agree, of the utility of zero-power finders. The most famous is probably the Telrad. These devices don't magnify. Instead, they project a pattern, usually 3 concentric red circles, onto a small window you look through.
Oh yeah, those are great. It looks like the circles are floating out there on the actual sky, right? Representing fields of view like 4 degrees, 2 degrees, half a degree.
Exactly. So you look at your wide field chart, see where your target is relative to bright stars, then you look through the Telrad and just move the scope until those projected circles line up with those same bright stars on the real sky. It makes pointing much more intuitive.
Okay, so you've used your charts, used your finder, and you've got something in the eyepiece. Now comes another fundamental skill, figuring out directions in the eyepiece view. Which way is north, west?
This is crucial, especially if you're star hopping or sketching. Coe's method is simple but effective. especially for mounts with tracking motors. First, you turn off the motor drive. Then you just watch which way a star drifts across the field of view. Because the sky appears to rotate east to west, the direction the star drifts towards the edge is always west. Always. Once you know west, the opposite direction where the star entered the field must be east. North and south are then simply perpendicular to that east-west line. Takes just a few seconds to orient yourself every time.
That's a neat trick. Now, for finding really faint stuff, especially if you don't have a go-to scope, Ko talks about using mechanical setting circles. He admits they can be tricky for beginners, they require some practice and careful alignment, but they can be really useful for getting you close to a target. Can you walk us through the technique he describes, like using them to hop to a fainter object?
Sure. The basic idea is you use the circles to bridge the gap between coordinates and visual star hopping. First, you find a bright, easily identifiable star near your target. One whose precise coordinates, right ascension and declination, say Betelgeuse in Orion. You center Betelgeuse carefully in the eyepiece. Then you meticulously set your telescope's RA and DL circles to match Betelgeuse's known coordinates. Now your circles are calibrated, at least roughly. Then you look up the coordinates of your actual target, maybe the nearby cluster NGC 2169. You carefully move the telescope, watching the setting circles until they read the coordinates for NGC 2169. Now, it might not be perfectly centered due to alignment inaccuracies, but it should be very close, probably within the field of view of your finder scope, or maybe even your low-power eyepiece.
Ah, okay. So you use the circles for the big jump, and then you might do a final small star hop from a nearby star the circles got you to, like New Orionis in his example, to nail NGC 2169 itself.
Precisely. It's a way to navigate using coordinates when the target itself is too faint to see in the finder.
All right, let's dive into what Ko calls the most important accessory you'll buy, the eyepiece. This is really where the magic happens, connecting the telescope to your eye. He breaks down the key things you need to understand about them.
Yeah, the eyepiece is critical. He defines three main parameters that are all linked together. First, obviously, is focal length, FL. This is usually printed right on the eyepiece, in millimeters. Long focal lengths, say 40 millimeters down to maybe 24 millimeters, give you low magnification and a wide field of view. Great for sweeping star fields or finding objects initially. Short focal lengths, maybe 8 millimeters down to 4 millimeters or even less, give you high magnification and a much smaller field of view. These are for looking at detail, but they demand good atmospheric seeing. And magnification is just a simple calculation. You take the telescope's main focal length and divide it by the eyepiece's focal length. Easy.
Okay, focal length and magnification. Then there's the exit pupil. This sounds a bit more technical. What is that exactly?
The exit pupil is basically the little beam of light that comes out of the eyepiece and enters your eye's pupil. Its diameter is important. You calculate it by dividing the eyepiece focal length by the telescope's focal ratio, the fun number. Now, a young, fully dark-adapted eye might have a pupil that dilates to about 7 millimeters. If the exit pupil coming out of your eyepiece is larger than 7 millimeters, say 8 millimeters, then some of that light cone is actually hitting your iris, not entering your pupil. You're essentially wasting light and aperture.
Ah, okay, so you want the exit pupil to be no larger than your eye's pupil. But Ko mentioned something specific here, this magic 2 millimeter exit pupil. What's special about 2 millimeter?
This is a really insightful point he makes, linking exit pupil to visual contrast. See, a really large exit pupil, like 5 millimeter or 7 millimeter, delivers a very bright image background. The sky itself looks brighter. This can be good for spotting extremely faint, large, low surface brightness nebulae where you just need maximum light throughput. However, that bright background can actually wash out the subtle details, the faint modeling in a galaxy's arms, or the structure near the core of a globular cluster. Reducing the exit pupil down to around 2 millimeter often darkens the sky background significantly. This increases the contrast between the faint object and the sky, making those subtle structures pop into view much more easily. It's often the sweet spot for galaxies and clusters.
That's a fantastic piece of practical advice. So thinking about buying eyepieces, especially for someone starting out, what's Ko's recommendation? Does he suggest getting a whole set right away?
No, not at all. His advice is very practical. Start with 3 good quality eyepieces. One for low power, maybe in the 25-40 millimeter range. One for medium power, perhaps 12-15 millimeter. And one for high power, say 6-9 millimeter. And crucially, combine these with a good 1.8x or 2x Barlow lens.
Right, the Barlow lens. It basically doubles the magnification of any eyepiece you put it in, right?
Exactly. So those 3 eyepieces effectively become 6 different magnifications when paired with the Barlow. But here's the really clever bit, the expert insight Co provides on Barlow's. A Barlow increases the magnification, but it does so while maintaining the original eye relief of the eyepiece you're using it with.
Eye relief. That's how far your eye has to be from the lens to see the full field of view.
Precisely. And very short focal length eyepieces, the ones needed for high power on their own, often have notoriously short, uncomfortable eye relief. You feel like your eyeball is almost touching the glass. Using a medium power eyepiece, which usually has comfortable eye relief, in a Barlow gives you that same high magnification, but you retain the comfortable viewing distance. It makes high power observing much more pleasant.
That's a huge practical advantage. Now, what about different eyepiece designs? He mentions Plessels, orthoscopics, Naglers. Are there big differences?
Yes, there are trade-offs in design, performance, and cost. The Plessel is a very common, good all-around design. Decent field of view, maybe 50-55 degrees, pretty good correction across the field, usually quite affordable. Their main drawback is that the eye relief gets tight on the shorter focal length versions. Orthoscopics, orthos, are an older design known for excellent sharpness, contrast, and a very flat field of view. They often have a narrower apparent field, maybe 40-45 degrees, but are superb for planetary or double star work where maximum detail is key. And then you have what Koo calls the Nagler revolution, started by Al Nagler. These eyepieces introduce ultra-wide apparent fields of view, 80 degrees or even more.
Wow, like looking out a spaceship window?
Kind of. It gives this very immersive spacewalk feeling, but they tend to be large, heavy, and significantly more expensive. So different designs for different priorities and budgets.
Okay, makes sense. Now let's talk filters. Specifically, light pollution reduction, LPR filters. For anyone observing near a city or even suburbs, these seem almost essential. How do they work?
They're pretty clever, actually. They work by exploiting the physics of light emission. Most common light pollution sources, like sodium vapor streetlights, emit light over broad parts of the spectrum, especially in the yellow and orange regions. But the light from emission nebulae, the things we really want to see, is concentrated in very specific, narrow wavelengths. The most important ones visually are hydrogen alpha in the red, and especially oxygen the third, O3, in the blue-green part of the spectrum.
Ah, so the filter acts like a gatekeeper. It blocks the broad yellow-orange light pollution, but lets the specific narrow green-blued wavelengths from the nebula pass through.
Exactly. It increases the contrast between the nebula and the now darkened sky background, making the nebula much easier to see.
So are all LPR filters the same? Co mentions different types?
No, they vary by how much light they block and which wavelengths they let through. He categorizes them mainly by their bandwidth. Wideband filters have a broader pass band. They cut out the worst light pollution peaks, but still let a fair amount of starlight through. They give a more natural view and are often preferred for astrophotography. Narrowband filters are the real workhorses for visual observing of nebulae. Things like the UHC ultra-high contrast filter or Lumicon's deep sky filter or Orion's ultrablock. These have much narrower passbands, centered on the key Obel 3 and H beta lines. They dramatically boost nebula contrast, but they do dim stars noticeably. And finally, you have line filters. These are extremely narrow, designed to pass only one specific emission line, like O4 or H beta.
Okay, why would you need such a specific filter, like just H beta?
Because some nebulae emit almost all their visible light in just that one wavelength. The classic example Co gives is the California nebula, NGC 1499. It's practically invisible without an H beta filter because its light output is overwhelmingly H beta. A standard UHC filter just won't show it. Same goes for the Horsehead Nebula.
Got it. So you might need specific filters for specific targets, but there's always a trade-off, right? Filters block light.
Absolutely. Co makes this crucial point. All LPR filters, by their very nature, will dim stars. You can expect at least a 1 magnitude loss in star brightness, sometimes more with the narrower filters. So you gain nebula contrast, which is usually the goal, but you lose some of the fainter stars in the field. It's a compromise. Hashtag tag 2.3 telescope maintenance and field practices. Moving on to keeping your equipment in top shape and using it effectively in the field. Co offers some really crucial operational advice. One of the most important is setting up your telescope early, ideally before the sun even sets.
Why so early? Is it just about having daylight to set up?
That helps, but the main reason is to allow the telescope's primary mirror to cool down and reach the same temperature as the surrounding night air. He calls it letting the mirror air out.
Ah, okay. What happens if the mirror is warmer than the air?
You get air currents rising off the warmer mirror surface and flowing up inside the telescope tube. These are called tube currents. They act just like the heat haze you see rising off asphalt on a hot day. They blur and distort the image, sometimes quite severely. Letting the scope sit and acclimate for an hour, maybe even two, before you start serious observing makes a huge difference to getting sharp, steady views.
That's vital to know. And what about actual cleaning? Mirrors get dusty eventually. Ko provides his method for the annual mirror clean. It sounds a bit daunting.
It requires care, definitely, but his process is quite straightforward. He recommends doing it about once a year unless it gets really dirty. First step, carefully remove the mirror cell. Then soak the mirror, face up, in a basin of distilled water with just a tiny drop or two of mild dish soap, like Dawn. This loosens the dust without scrubbing.
Okay, soak, don't scrub. What next?
After soaking for a while, you gently wipe the surface using sterile cotton balls. Just drag them slowly across the surface under their own weight, maybe once or twice. No pressure. The goal is just to lift off the loosened grime.
Right, super gentle. Then rinse.
Yes, and this is a key step. Rinse thoroughly with plain distilled water first. Then, for the final rinse, use a mixture of 5 parts distilled water to 1 part pure isopropyl alcohol, 91% or higher.
Why the alcohol mix?
The alcohol helps the water sheet off the mirror surface evenly, preventing water spots from forming as it dries. You just hold the mirror nearly vertical and let the mixture run off, then let it air dry completely.
Okay, that sounds manageable with enough care. Now, Ko also talks about telescopes themselves and this thing called aperture fever, the constant desire for a bigger scope. He owned big ones himself, right? A 17.5-inch, then a 13-inch.
He did, and he acknowledges the allure. Bigger mirrors gather more light and offer higher resolution, letting you see fainter details. But he strongly emphasizes that you shouldn't dismiss smaller telescopes. In fact, he argues that small scopes, say in the 3-inch to 6-inch range, especially those with faster focal ratios like f6 or f8 or less, are absolutely wonderful rich field instruments.
Rich field, meaning wide fields of view.
Exactly. They provide these stunning, expansive views of the sky. They allow you to frame really large objects like the entire North American nebula, NGC 7000, or the Andromeda Galaxy with its companions, all within a single eyepiece view. That's something a giant, long focal length telescope often struggles to do, so small scopes have their own unique and valuable place.
That's good perspective. And this actually leads perfectly into maybe the most important practical lesson Ko shares, wrapped up in a hilarious, almost disastrous anecdote. And the lesson is, always test new equipment at home first.
Oh, this story's a classic. Tell it.
Okay, so Ko borrows this big telescope, a 12.5-inch Newtonian. He's excited, loads it into his car, drives hours out to a really remote dark site in Arizona. He gets it all set up under the stars, and then realizes the eyepiece, when pointed high up, is way, way above his head. And guess what he forgot?
The stepladder.
Exactly, no stepladder. He's miles from anywhere. So he's looking around in the dark, desperate for something to stand on, and he spots his friend AJ's spare tire lying nearby. Perfect, he thinks.
Uh-oh. I sense where this is going.
He drags the tire over, uses it as a makeshift step stool. He gets up there, starts observing, totally focused on the eyepiece, balancing precariously in the pitch black. And then he shifts his weight slightly, loses his balance a bit, and slams his foot down hard right onto the tire's air valve stem.
Oh, no.
Instantly, there's this loud, violent Aisha as all the air rushes out of the tire. Now, remember, it's pitch black, he's tired, he's in the Arizona desert. What's the first thing that flashes into his mind?
Rattlesnake.
Bingo! He's absolutely convinced he just stepped on a giant rattlesnake. He said he literally leaped into the air, yelling, flailing, and came incredibly close to knocking over and destroying the entire large telescope in his panic.
That is terrifyingly funny. But the moral is crystal clear.
Absolutely. Know your equipment before you get to the dark site. Know how tall it is, what accessories you need, how heavy it is. Test everything in your backyard first.
All right. We've covered the observer, the conditions, the gear. Let's finally get to the good stuff. The deep sky objects themselves. What are we actually looking for? What kinds of details can we realistically expect to see? Let's start with the grandest structures. Galaxies.
Sounds good. Coop helpfully organizes galaxies using Edwin Hubble's famous classification scheme, the tuning fork diagram, ellipticals, spirals, barred spirals, irregulars. And understanding this basic classification is really useful for the visual observer because it sets expectations about what kind of structure or lack thereof you might see. Exactly. And this is a key insight Cope provides for visual observing. Elliptical galaxies, which Hubble classified from E0, perfectly round, to E7, highly elongated, visually they tend to look very smooth, almost featureless. That's because they're mostly made up of older stars, what astronomers call population 2 stars. These are generally cooler, reddish, and formed early in the universe when there weren't many heavy elements around. No gas, no dust, no new star formation, just a smooth glow.
Right. But then you get to the spiral galaxies, SE, SV, SC, and the barred spirals, SBA, SBS, SEC. These are completely different visually because they contain large amounts of gas and dust, and they're actively forming new stars, hot, young, blue, population-ized stars. You can actually start to see structure. You might see modeling in the arms, maybe hints of dust lanes, brighter knots, which are huge star-forming regions, HEI regions. That visible texture tells you it's a living, evolving galaxy. That's the detail you're hunting for.
Okay, let's make this concrete. Can you give an example target? Co mentions NGC 4565.
Ah, yes, the spindle galaxy in Coma Berenices, a
Ah.
fantastic target. It's a classic edge-on spiral galaxy, very long and thin, maybe a 7-to-1 ratio, and has quite a high surface brightness, which helps. Kuhn notes that in a decent-sized scope, say 13 inches or so, the prominent dark dust lane that cuts right through the central bulge is easy to see. It just slices the galaxy in half.
Wow. And can you see more detail than just the dust lane?
With good seeing and careful observation, especially using averted vision.
Yes.
He mentions being able to detect scallop detail along the edges of the galaxy. That scalloping is actually the subtle structure of the spiral arms seen edge-on, silhouetted against the brighter bulge. That's a challenging but rewarding detail.
Cool. And then there are the barred spirals. You mentioned the Milky Way is now thought to be one. What do they look like visually? He gives NGC 1365 as an example.
Right. Barred spirals are fascinating, sometimes quite bizarre looking. They have this strong linear bar of stars running through the center, instead of just a round bulge. In a galaxy like NGC 1365, though that's a tough southern hemisphere object, or others like M95, you can actually see the bar clearly. And sometimes the spiral arms seem to spring from the ends of the bar, rather than the center. Coe describes the appearance of some barred spirals with curved glows attached to the bar ends as looking like a two-armed garden sprinkler, a very memorable, distinct shape compared to regular spirals. Okay, moving on from galaxies, let's talk about nebulae, those beautiful clouds of glowing gas and dust. Coe differentiates between the two main types you'll encounter visually.
Right. First up are the emission nebulae. These are the really dramatic ones, aren't they? Like the Orion Nebula?
Exactly. They glow because the gas itself, mostly hydrogen, is being energized. It's getting zapped by intense ultraviolet radiation from very hot, young, massive stars that have recently formed within or nearby the nebula.
So the UV light strips electrons off the atom's ionization, and when the electrons recombine, they give off light.
Precisely. And they emit that light only at very specific wavelengths, dictated by the physics of the atoms involved. The most famous is the red light of hydrogen alpha. But visually, the most important is often the blue-green light from doubly ionized oxygen, called O3.
And those specific wavelengths are why the narrowband filters, especially the O3 filters, work so well on these objects, right?
Absolutely. They isolate that specific O3 light, making the nebula stand out dramatically against the filtered sky.
Okay, so that's emission nebulae. What's the other main type?
The other type are reflection nebulae. These are much simpler conceptually and visually. They don't generate their own light at all. They are basically just clouds of interstellar dust. And if there happens to be a bright star or stars nearby, the dust cloud simply scatters the starlight.
Like fog scattering headlight beams.
Exactly like that. And because dust scatters blue light more effectively than red light, reflection nebulae typically appear bluish in color. The classic example Coe gives is the faint, wispy nebulosity surrounding the stars in the Pleiades star cluster, M45. That haze around Merope and Maya, that's NGC 1432 and 1435 pure reflection nebula.
Gotcha. Now, let's tackle a really challenging emission nebula target he discusses. The California Nebula, NGC 1499. Photographs make it look amazing, shaped just like the state. But visually, it's known for being incredibly tough to see. Why is that?
Two main reasons. It's absolutely huge on the sky, several degrees long, and it has an extremely low surface brightness. It's very faint and spread out.
So a high-power view and a big scope is probably the wrong approach.
Definitely. Coe advises that it's best viewed with very wide field instruments.
Yeah.
Think binoculars like 7x50s or 10x50s, or maybe even just at the finder scope on your main telescope. You need that wide perspective.
And the filter, you mentioned this earlier.
And crucially, yes, you absolutely need that specialized H-beta filter. As we discussed, the California Nebula emits almost all its visible light in that narrow H-beta wavelength. Without that specific filter, even under perfect skies, you'll likely see nothing at all. It's a filter-dependent object.
Okay. And within nebulae, there's a special category. Supernova remnants, the leftovers of exploded stars.
Yes, the expanding shells of gas thrown off when a massive star dies catastrophically. And Coe uses these objects to highlight something really profound, a concept he calls the grand plan of cosmic recycling and distribution.
What's the core idea there?
It's the realization that virtually all the elements heavier than hydrogen and helium, everything that makes up planets and indeed us, were created inside massive stars through nuclear fusion. Carbon, oxygen, nitrogen, silicon, iron, all of it. But it would just stay locked inside those stars unless there was a way to get it out.
And the supernova is the delivery mechanism.
Exactly. The explosion blasts these newly forged heavy elements out into interstellar space, enriching the gas clouds from which future generations of stars and planets will form. So the calcium in your bones, the iron in your blood, every heavy atom in your body was cooked inside a star and ejected by a supernova billions of years ago.
That's incredible. So when we look at a supernova remnant, like the Veil Nebula in Cygnus,
NGC 6992 and the rest of the Cygnus loop, yes. A truly spectacular sight, especially with an O3 filter. It's huge, delicate, filamentary. When you look at the Veil, you are literally seeing the scattered remains of the stellar factory that produced the raw materials necessary for life itself. You're watching that cosmic distribution plan in action. Hashtag 3.3 planetary nebulae and star clusters. All right, let's move to another fascinating class of object, planetary nebulae, or PNs. Now, despite the name, they have absolutely nothing to do with planets. William Herschel coined the term back in the 1780s because in his small, relatively low-power telescopes, they often appeared as small, greenish or bluish, somewhat disk-like objects, vaguely resembling planets like Uranus, which he had recently discovered.
so what are they really?
They represent the final, luminous end stage in the life of stars like our own sun. Our sun will eventually become one, probably in about 5 billion years. They are the cast-off outer layers of a dying, medium-mass star.
And they glow quite brightly, often with distinct colors. What makes them shine? Is it the same as emission nebulae?
Similar. But the mechanism Coe describes is a bit different and really interesting, leading to their typical shapes. First, as the star ages and expands into a red giant, it sheds its outer layers relatively slowly, creating this large, expanding shell or envelope of gas, the slow wind. This often forms a sort of barrel shape due to the star's rotation or magnetic fields. Then, the star's hot, exposed core emits a much, much faster stellar wind particles, traveling at incredible speeds, maybe 1,000 to 4,000 kilometers per second.
Wow, so this fast wind slams into the slower wind that was blown off earlier?
Exactly. It's like a snowplow hitting a snowdrift. This high-speed collision violently compresses and heats the gas in the shell, causing it to glow intensely. It's not just photonization like in HII regions, but also collisional excitation. And this process is particularly good at making oxygen the third shine brightly, giving many PNs that characteristic blue-green color.
That explains the structure and color. Can you give us a good visual example?
A beautiful one is NGC 3242, often called the Ghost of Jupiter Nebula. It really shows off that striking blue-green O3 color. And Coe notes that in larger telescopes, you can start to resolve the structure created by those colliding winds. You might see a bright inner ring, the main collision zone, possibly surrounded by a fainter, more extended outer envelope or halo, sometimes with a slightly different pinkish hue from hydrogen alpha. It can look like a celestial bullseye.
Fantastic. Okay, last category, star clusters. Coe can contrast the two main types we see, open clusters, OC, and globular clusters, GC. How do they differ visually?
They look and are fundamentally different. Open clusters are generally young, relatively small collections of stars, maybe dozens to a few thousand. They formed together recently from the same giant molecular cloud, so they are typically found within the disk of our Milky Way galaxy. Because they're young, they contain stars rich in heavy elements, and this leads to a wide variety of stellar colors being visible: bright blue, massive stars, yellow sun-like stars, maybe some older orange or red giants. Think of the Pleiades or the Hyades.
And they often look quite loose, irregularly shaped.
Yes, they're usually not very tightly bound by gravity and tend to disperse over hundreds of millions of years. Coe mentions the Trumpler classification system for OCs, which describes their concentration, loose to dense, the range and brightness of the stars, and how rich the cluster is, number of stars.
Okay, so open clusters are young, colorful, and relatively nearby in the galactic disk. What about globular clusters?
Globulars are the complete opposite in almost every way. They're ancient, truly ancient. Many formed very early in the universe's history, 10 to 13 billion years ago, so they're almost as old as the galaxy itself. They contain hundreds of thousands, sometimes millions of stars packed into a very tight spherical volume. And these are population 2 stars, very old and, crucially, very metal poor. They formed before many heavy elements have been created and distributed by supernovae.
And that affects their appearance.
Absolutely. Because they lack those heavy elements, you don't see the wide range of colors like in open clusters. Globular cluster stars overwhelmingly appear whitish or slightly yellowish.
And they look so densely packed, especially towards the core. Are the stars actually almost touching?
That's mostly an illusion caused by their immense distance. Globular clusters orbit far out in the halo of our galaxy, much further away than most open clusters. So while they're densely packed compared to the solar neighborhood, the stars are still light years apart. But from Earth, they look incredibly compressed, especially in larger telescopes, where you can start to resolve individual stars even near the core.
So what's a prime example of a globular cluster that really shows off these features?
Well, the undisputed king of the northern hemisphere globulars has to be M13, the great globular cluster in Hercules. It's visible even in binoculars as a fuzzy patch. It contains maybe 500,000 stars. Coe shares some observation notes taken with a huge 36-inch telescope, which really convey the detail possible. He describes seeing many, many beautiful chains and tendrils of stars radiating out from the main ball, almost like glittering tentacles.
Wow, chains of stars.
Yeah, these arc-like arrangements. And he also noted that a famous dark feature near the core, a sort of three-vein shape known as the propeller, was easily visible using averted vision in that large scope.
Incredible. Seeing that kind of intricate structure in something so ancient and distant, that's really the payoff for all the preparation and technique, isn't it?
That's exactly what deep sky observing is all about. Hashtag Yoche outro.
Well, this has been an absolutely fantastic deep dive. We've really covered the whole gamut, haven't we? From, picking the right spot and making sure your scope is cooled down to training your eye with those specific NGC codes, checking the seeing, and then knowing what actual details to look for in galaxies versus nebulae versus clusters. It's a lot, but it all connects. And it really comes back to that guiding principle from Coe that you mentioned earlier. Astronomy should be a joyous hobby, not a second job. All this preparation, all these techniques, they're not meant to be burdensome. They're the keys to unlocking that joy, to maximizing what you can actually see and appreciate out there.
Well said. And maybe going to leave you, the listener, with one final thought to ponder. Something that really ties together the vastness and the meaning of what we've been looking at. Just take a moment to reflect on the sheer scale of time and space involved in this deep dive. You've looked back billions of years at the light from ancient globular clusters, whose stars were among the first to form. You've gazed upon the nebulae, these stellar nurseries, where gas and dust are actively collapsing right now to form new suns and perhaps new planets.
And that connection to supernovae, that's the one that always gets me. The idea that the stuff of life wasn't made in the Big Bang, it had to be manufactured later inside stars. The iron that carries oxygen in our blood, the calcium that makes our bones strong, all forged in stellar cores, and then violently scattered across the galaxy by those supernova explosions we see remnants of, like the Veil Nebula.
Exactly. So when you look up at that faint, expanding shell of gas from an ancient stellar explosion, you're literally looking at the aftermath of the process that created the atoms that make you you. The next time you point your telescope towards the deep sky, remember that. You're not just looking out into space. In a very real sense, you are staring directly into your own chemical origins, your own cosmic past.
That's a powerful thought to end on. Go look up, everyone. And if you're hungry for even more detail, Coe lists further reading and advanced resources in Chapter 18 of Deep Sky Observing. Definitely check that out. Until next time, happy observing, and we wish you crystal clear skies.